In the previous lecture, we have studied about the first type of pulse communication technique, which is pulse amplitude modulation, and we have highlighted some drawbacks of it. That the information is contained in the amplitude, and because of that, interference of the noise is maximum. The peak power required by the transmitter varies since the amplitude is varied in PAM. Now, to overcome this particular drawback, we are going for the second type of pulse modulation technique, which is called as pulse width modulation. The definition of PWM is it is the process in which the width of the carrier pulse train is changed in accordance with instantaneous amplitude of modulating signal, keeping amplitude and position of the carrier pulse train constant. So in the PAM, we are changing amplitude, keeping width and position constant. In PWM, we are changing width, keeping amplitude and position constant. Other wordings for the definitions will remain same. So here we are going to change the width, and this particular advantage will have a big application in our industries. Now, if we see the waveforms of PWM, then we have this as the modulating signal. Then we have a carrier sampling pulses, and the output of PWM you can see in this graph, wherein you can see the width of the pulse is changing, and this particular width is drawn when the amplitude of the modulating signal is maximum. The width of the pulse is maximum, and when the amplitude of the modulating signal is minimum, the width of the pulse is minimum. And that is why this particular is called as, you can see throughout the graph, the amplitude is not changing, only the width of the pulse will change, and that is why this is called as pulse width modulation. Now let us understand the basic principle of PWM with the help of this graph, that actually how PWM signal is getting generated. So you can see there is a triangular wave which is marked with the black color. There are three levels, A, B and C is marked with a different color. So what happens is when the triangular wave crosses each of the level, suppose consider that only A level is marked. So when the triangular wave, originally the output is 0. When triangular wave crosses this particular point A, the output changes from 0 to 1. It will remain in that one position when, unless the triangular wave again crosses that particular A line, that time you are getting again a fall in the output. Similar to that, when the triangular wave crosses B line, you are getting this red pulse. When triangular wave is crossing this blue line, that time you are getting this wider pulse. Meaning, how PWM signal will be generated? With the help of comparison of the two signals. So here, which are the two signals? One is the triangular wave, another is this DC reference lines. And with the help of that, you can see we are getting PWM signal. The red color pulse indicates red line, black color indicates black line, and this blue color indicates blue line. And that is how the PWM signal will be generated. So this is the principle of generation of PWM signal by comparison of the two waveforms, and the same principle we are going to use in the circuit diagram. So you can see clearly here, this is a comparator which is going to compare a sawtooth signal which is acting as a carrier, or you can say second waveform, and the modulating signal is applied to the non-inverting terminal. Carrier is applied to the sawtooth generation signal is applied to the inverting terminal. Output of the comparator will be PWM signal. And this particular comparison is done here similar to the previous, that how we have done superimposing of the two waveform. Similar way here also, first the sawtooth waveform is drawn, then randomly the modulating signal is drawn onto this. Now you can see modulating signal is given to the non-inverting terminal and sawtooth generation is given to inverting terminal. So output of comparator will remain low unless and until modulating signal amplitude is increasing beyond the sawtooth waveform. So when the modulating signal amplitude increases beyond sawtooth generation waveform, then the output of comparator will be high. For all other cases, output will be low. So you can see at this particular point, the output is becoming from low to high. Till what point it will remain high? Till the modulating signal amplitude is lower than the sawtooth signal. So at this particular point, what happens? Sawtooth signal crosses the modulating signal. Modulating signal is still negative, but sawtooth goes positive, and that is why you get output low. It will remain low unless it will remain low. Again, now at this particular point, you see modulating signal amplitude is high, the sawtooth wave amplitude is low. Output goes from low to high. Because modulating is applied at non-inverting, output will go only high when the modulating signal goes high as compared to sawtooth waveform. So during this particular region, the modulating signal is high, sawtooth is low, output is triggering from 0 to 1. It will remain in this particular state till again the sawtooth signal is going beyond the modulating signal. Again it will go low. And this is how, when you compare this particular two waveform, you are getting pulse width modulated signal at the output. And this is just by comparison of modulating signal and sawtooth signal. Sawtooth is applied at inverting terminal, and modulating is applied at non-inverting terminal of comparator. And output will be high only when modulating signal crosses the sawtooth generator. So at every instant you see the dot is marked where there is a crossing, the output is becoming high to low, and because of that you are getting PWM signal at the output. Now if we see the waveforms of the PWM, it looks like a pulse waveform which is having a variable duty cycle. Variable duty cycle means on and off time period is different, and because of that PWM waveform can be of 10% duty cycle, it can be of 50% duty cycle, it can be of 90% duty cycle, because you are changing on and off time period by changing the width of the pulse. The biggest application for the PWM signal is for the controlling of any devices such as motor, such as solenoid valves in the industry, such as any load in which the PWM signal is applied, because the output of PWM signal is variable duty cycle signal, and because of that PWM signals are used to control the amount of power which is transferred to the load. And because of that PWM finds application in the industry for controlling applications of motor, of valves, of any devices where the power transfer to the load is controlled. How it is controlled? Because it has variable duty cycle, it has different on and off time period, and because of that PWM signal will decide for how much time the supply should be given and for how much time it should be off. So when the period is on, when the on period is more, for 95% of time the supply is given, and for 5% time the supply is off. When the duty cycle is 50%, then for 50% supply will be given, 50% it is off. When duty cycle is 5%, then for only 5% the supply will be given, 95% supply will be off. And that is why I said that PWM is used for controlling the amount of power which is transferred to the load. And this is what is the application of PWM. So PWM में we are changing width of the pulse signal in accordance with instantaneous values of instantaneous amplitude of modulating signal, and because of that we get variable duty cycle waveforms at the output, which can be used in industrial application for controlling amount of power which is transferred to the load. In the next lecture we will be able to see about pulse position modulation.